Hi everyone, in this video we're going to talk about quantifying acidity and basicity by calculating pH. In order to understand pH, we really need to understand this process called the auto-ionization of water. And essentially, if we think about a glass of pure distilled water, while we might imagine nothing but water molecules being present, there is a process that occurs when two water molecules react to form a hydronium ion and a hydroxide ion. You can see essentially that one proton has been transferred from one water molecule to another, rendering an H3O plus ion, sort of like a water molecule with this extra proton, and the hydroxide ion, which is what's left over from water when H plus is removed. Now this equation shows what's occurring. Two water molecules react. Although sometimes we might simplify this and show it as one water molecule just breaking apart into a hydrogen ion and a hydroxide ion. And while that's often used to describe the auto-ionization of water, it is a bit of a simplification. So you might recognize one of the products of that reaction, H3O plus, is of course what we learned makes acids acidic. Even if we simplify it as H plus, when we learned about the Arrhenius definition of an acid, we know that it is the presence of hydrogen ions that makes a substance acidic. And it's the presence of hydroxide ions that makes a substance basic. So water can act like an acid or it can act like a base. A substance that can do that is called amphoteric. It should make sense that for water, we're always going to generate just as many hydronium ions as hydroxide ions. As long as it's pure water, therefore, we're going to have a neutral solution where the concentration of hydroxide is equal to the concentration of hydronium. Now, we want to think about how we quantify the concentrations of these ions. And of course, concentration is measured in molarity. So what's the molarity of hydronium in pure water? You might guess correctly that it's very, very small. The concentration of hydronium in pure water is 1 times 10 to the negative 7th molar. That's 1/10,000,000th of a mole per liter. Now, writing a molarity as 0.00000001 molar is kind of cumbersome. So instead, we're just going to say that this has a pH of 7, because that's the order of magnitude, or the exponent in the molarity is -7, 1 times 10 to the negative 7th. Since a logarithm is an inverse of an exponent, we can use a logarithmic scale to calculate and define pH. pH is defined as the negative logarithm of the molarity of hydronium in a solution. Those are the ions that make a solution acidic, and we'll measure their concentration as a pH, or a power of hydrogen. Now, the letter P is sometimes described as standing for power, or sometimes from the French word puissance d'hydroge, which means power of hydrogen, and sometimes potential of hydrogen, but it's defined mathematically as a negative logarithm of the concentration of hydronium ions. So if the concentration of hydronium ions is 0.000001 molar, that means it has a pH of 7. It's 7 orders of magnitude away from 1 molar. So pH is calculated as the negative log of hydronium ion concentration. Now, hydronium ion concentration is the more formal definition. Sometimes you'll see it written as just H plus concentration, and these can be used interchangeably. So don't let that confuse you if you see the equation written this way. The H plus ion is just a shorthand for writing H3O plus. Now, we can rearrange this equation to solve for H3O plus concentration. That would be 10 to the negative pH. Let's try a few calculations. First of all, let's see if we can calculate the pH of the following solutions. 1 times 10 to the negative 4 molar H plus. Let's see what that calculation would look like. I need to take the negative log of that molarity, the negative log of 1 times 10 to the negative 4th. And that gives me a pH of 4. How about 1 times 10 to the negative 5th molar hydronium? I need the negative log of that molarity, the negative log of 1 times 10 to the negative 5th, pH of 5. How about the pH of the solution that's 7.3 times 10 to the negative 4th molar in hydronium? Can you guess whether this will be between 4 and 5, or less than 4, or greater than 5? Let's do the calculation. The negative log of that concentration, 7.3 times 10 to the negative fourth, is going to give me a number that's less than 4. And that should make sense. This solution is even more concentrated in hydronium than the first. And notice its pH is lower. A lower pH corresponds to a higher concentration in hydronium. Let's do another type of calculation. In this calculation, we're asked to determine the hydrogen ion concentration when we're given a pH. If the pH of a solution is 5.85, what's the concentration of hydronium? Here we need to use the equation 10 to the power of a negative 5.85 using the concentration of hydronium in this solution. So now that we've looked at a few calculations, let's wrap this up and just make sure we understand the concepts and why a logarithmic scale is appropriate. We know that in pure water, there's got to be just as much hydronium as hydroxide. And we know the concentration of hydronium is 1 times 10 to the negative 7th molar. Therefore, the concentration of hydroxide is the same. That's 0.000001 molar, 1 times 10 to the negative 7th. 1 in 10 million moles per liter. Now, we say that the pH is 7, the negative log of that concentration. It's interesting to note that the product of hydronium ion concentration and hydroxide ion concentration is always the same, 1 times 10 to the negative 14th. And if we calculated pOH, that is the negative log of hydroxide ion concentration, we'd see that pH and pOH always add up to 14. This is not only the case for pure water, but for any aqueous solution. For instance, let's look at an acidic solution. In an acidic solution, there'll be more hydronium than hydroxide, and the pH will be less than 7. For instance, if the pH of the solution is 5, that means the concentration is 0.00001 molar in hydronium. A pH of 5 means the concentration is 1 times 10 to the negative 5th molar in hydronium. That means the concentration of hydroxide will be much smaller. Again, the pH and the pOH will always sum to 14. And the product of the molarities of hydronium and hydroxide will always be a constant we call Kw. How about, for instance, in a basic solution? In a basic solution, there'll be more hydroxide than hydronium, and the pH will be greater than 7. For instance, if the pH is 11, that means the hydronium ion concentration is 1 times 10 to the negative 11th. The hydroxide ion concentration will be much greater, 1 times 10 to the negative 3rd. Notice those two exponents sum to 14, and that reinforces the idea that pH and pOH will always sum to 14, and the product of these two ions' concentrations will always be a constant. As a result, we get a pH scale that ranges from 0 to 14 for most cases, and it's a measure of how acidic or basic a substance is. It really quantifies the hydronium ion concentration as an order of magnitude. Notice that the more acidic something is, the less basic something is, in that the more hydronium there is, then the less hydroxide, and vice versa. If something is very basic, it's got very little hydronium and an excess of hydroxide. So to summarize, in a solution of pure water, then some of the water molecules will ionize to form equal amounts of hydronium and hydroxide. But in other solutions that are acidic or basic, there'll be different amounts of hydronium than hydroxide. If there's more hydronium, which are the molecules or species which make a substance acidic, we calculate pH as the negative log of hydronium ions. If, on the other hand, there's more hydroxide than hydronium, the solution be classified as basic. We can also calculate the concentration of hydroxide ions and derive a term called pOH. pOH is the negative log of hydroxide ions. The sum of pH and pOH will always be 14 for any solution. So pH is a way for us to quantify acidity or basicity. And of course, things that are especially acidic or especially basic are both corrosive. It's important to remember that both strength and concentration determine pH. So a weak acid can be dangerously concentrated, and a strong acid can be diluted to the point where its pH is not especially low. Let's wrap this up with a quick look at a PHET app. So in this PHET app, we're modeling water first, and you can see that in the water, there's very few hydronium and hydroxide ions shown. I'm going to select solvent, and the solvent is water. All these gray molecules in the background, you can see there's many, many, many times more solvent molecules, water molecules, than there are hydronium or hydroxide. As a matter of fact, it's almost impossible to represent this graphically, since there should only be one red and one blue for every 10 million of the other gray ones here. Maybe a graph would help. Even the graph is going to be ineffective unless we use a logarithmic scale like this one is doing. Notice the gray bar here represents the concentration of water, and the red and blue bars represent the concentrations of hydronium and hydroxide. But the y-axis here is not going 0, 1, 2, 3, but rather 1, 1/10th, 100th, 1,000th, 10,000th, 100,000th, millionth, 10 millionth, because there's only 1 in 10 million moles per liter of hydronium or hydroxide. Now let's look instead at a strong acid. And you'll notice when we look at a strong acid, of course, the pH is going to be lower. A low pH means an acidic solution. Here, the red ions represent hydronium, but the blue ions do not represent hydroxide. They represent the conjugate base of the acid. You can see that the concentration of hydronium is much greater in a solution of a strong acid than it is in water, and so of course the pH is very low. How about a weak acid? Remember, a weak acid, even if it's the same concentration, will not ionize completely, and so there are fewer hydronium ions, and the pH is higher. It's less acidic. The blue molecules here are the conjugate base of the weak acid. The red ones are hydronium, and the dark gray ones are the undissociated or unionized form of the molecular weak acid. Hopefully it makes sense that water has a pH of 7, the strong acid has a pH of 2, and the weak acid has a pH that's a little bit higher than 2. Now, concentration will also affect pH, but acid strength and acid concentration are not the same thing. So I hope that was a helpful introduction to the pH scale. We'll see you next time.